Okay, so now I want to talk about what this surface looks like in 2 and 3D. So we're going to look and compare the Tresca and the von Mises surfaces. So these are going to be the yield surfaces. And I'm going to start in 2D because we can draw some better pictures here. So here is what this is going to look like in 2D. I'm going to do my best here to draw something that is close to being the right shape. Okay, there's the y-axis, perpendicular x-axis there. We're going to hope that that's going to be big enough. We're going to go through and draw these squares. That's going to be about the right size. Okay. And so this is going to be the Tresca failure surface. Remember, we're now talking about a principal stress space. So this is going to be sigma 1 over sigma y. This is going to be sigma 2 over sigma y. And my Tresca failure surface, which again, this is a yield surface, so this is when the material would yield. It's going to go from 1 and 1 on the positive side, negative 1 on in the fourth quadrant here, sorry, the third quadrant. And it should have a surface that looks something like this. Okay, so that's the Tresca envelope that we talked about before. So what about the von Mises? What does that look like? Well, the von Mises, let me see if I can draw that here, is close, so it's going to actually touch at these 3 points and these 3. And then I'm going to try and just give myself a couple of kind of reference dots here, so see if I can get this pretty close. So we're going to come up, we're going to come across, come up, and then we're going to hit there, come around, hit there, across and over. That should be smooth, sorry. And there's the last one. So, this is going to be our von Mises. And it should be an ellipse. I apologize for the poor drawing here. So the light blue is Tresca, the dark blue is the von Mises surface. So you can see that some two kind of points here. So the von Mises is more comprehensive. So it is taking into account the strain energy to V. And the Tresca is more conservative. So it's certainly simple, and it is more conservative. And to have an example here, what we'll do is we'll think about the state of pure shear. So if you have pure shear, you'll actually come down this way. And so we'll be looking at those 2 points and where they are. But this line is going to be pure shear. And when you have a pure shear case, sigma 1 is going to be equal to the opposite of sigma 2, which is going to be equal to tau. So we'll call that shear stress tau. And we can go back and we can calculate what these two limits are. So I'm going to use the equalities, and we would recognize that we'd have to be less than that. Tresca, we would say that we have a sigma 1 and a sigma 2. So sigma 1 would be our larger positive value. Sigma 3 would be minus a negative value, negative tau in this case. And that's going to be equal to sigma y. That's our limit. So that would tell us that the limit on tau, so that would be tau y, is going to be equal to sigma y over 2. So that would be for our Tresca. This is our Tresca. And you can see that's this point right here. It's halfway. The other one that we're going to look at is von Mises. And we said that for a state of plane stress, we had an expression like this. So this is sigma y squared. We're going to have a sigma 1 squared, so that's tau squared. And it's going to be minus sigma 1 times sigma 2. And then we're going to have plus tau, sigma 2 squared. So that's going to be negative tau squared. And if you put all that together, this ends up giving you 3 tau squared at the end of it. So we would get that tau is equal to sigma y divided by the square root of 3. And so there you have it. The square root of 3 is a little bit larger, and you can see that in our picture here. So it's slightly more conserved to go with the Tresca, but it's slightly more comprehensive if you use the von Mises. So this is, I'm going to match up better with the test data that we have, and it's a little, you get a little bit more breathing room, so you would get a little bit higher capacity. But this tends to be a better estimate for yield than the Tresca, but it is a little more complicated, especially in full 3D. So now I want to look at these same surfaces, these same envelopes, but now in 3D. And so here's where things will probably get a little bit tricky. I'm going to do my best to draw this in 3D. The challenge is that you kind of have to trisect an angle, which turns out to be tough, but I'll do my best here. Okay. It's not bad. Could be worse. Okay, so this is going to be sigma 1. This is going to be sigma 2. This is going to be sigma 3. And so these are still 90-degree angles, but what we're doing is we're looking essentially directly at we're kind of looking down a line which is equal amounts of sigma 1, sigma 2, and sigma 3. So this is sigma 1 equals sigma 2 equals sigma 3. That's this line. This would be our isotropic pressure line. All right, so for any value of P, sigma 1 equals P, sigma 2 equals P, sigma 3 equals P, that would be this line. And it's coming straight out of the page. So to visualize the Tresca failure surface, I had done this last time. You can use a hexagon. And so if you were to look down this isotropic pressure line, you would see essentially a hexagon. And this would be your isotropic pressure line, my pen, and you could have any value of isotropic pressure, and you would still be inside of your surface. It's once you move in one of the principal stress directions by itself, that's when things are going to potentially yield. Okay, so that is the Tresca yield envelope. What would the von Mises look like in this same space? Well, it would be of similar size, but now instead of being a hexagon, see if I can do this, it's going to be a circle. And it's, of course, it's going to hit all the vertices of our Tresca envelope, but it's going to be circular. And I hope that you can sort of see what that looks like here. I could maybe scoot it over to the camera so you can see what that. So again, we're looking down this isotropic pressure line, And if I move it closer to where the camera is, maybe, there we go. What about there? You can see kind of what that's supposed to look like. Okay, so that's what that's going to look like in 3 dimensions. I just wanted to give you an idea of what that looks like. We're going to mostly be thinking about this stuff in 2 dimensions for the most part, but it is a 3-dimensional concept, and certainly it's good to have some idea of what that's going to look like.